Yeah, so the subtitle of my presentation is how to make deep learning basically to suck less. And anyone who ever trying to get something going with deep learning with all the libraries and dependencies knows that it's just a real pain. So hopefully after this session, you might be intrigued how you can actually reduce the pain a little bit. So Docker, in some sense, is a little bit the shipping container in the software development world. Shipping containers basically revolutionized how goods were shipped around the world by being standardized, having standardized sizes and whatnot. It just made it really easy getting in and out of ports and ships and whatnot. And if you have software containers, they basically package code and all its dependencies. And in theory, it runs quickly and reliably and can be basically moved between computing environments. And with a Docker container image, you basically package the code, runtime libraries, system tools, system libraries, and whatever settings are necessary for executing whatever code you have that needs running. At runtime, you basically then use an image, instantiate it, and you get basically what is a Docker container. And this Docker container nicely isolates the environment basically from the host system. And they're really lightweight compared to virtual machines. So whereas a virtual machine emulates hardware, Docker really only virtualizes the operating system. So you, rather than having a hypervisor like with virtual machines, you really just pass on through sort of like the kernel from the host system. And therefore you also have to use the same architecture that you have outside the system. So if you have an Intel architecture, then it means you can use Intel inside. If you have an ARM architecture, then ARM needs to be inside and outside, of course. That's the really basic overview. By not emulating hardware, those containers can start up a lot quicker, consume a lot less CPU cycles, and it makes it really nice running these things in parallel. So there are basically base images available for Windows and Linux. However, it was mainly that there are some available for Windows, mainly because it really took off with Linux. And then Microsoft just thought, hey, we'd like to do that as well. And then there was even official support available. But that, I think, is even by Microsoft now considered like deprecated again. I mean, I'm not surprised because Windows is rather broad and you can hardly sort of like strip that back, that you can run it on small devices and embedded devices like Linux. And if you look at an Alpine Linux image, they start at 5 megabytes disk space. So that's really, really tiny. I mean, it's really bare bones, but you can really do some things also in embedded systems with that as well. And considering that anything in the deep learning space and AI R&D really happens on Linux, there's no real point really doing anything in Windows. And of course, you have no license fees with GNU Linux. There is, so if you are running Windows on your machine, there is a potential solution which I can't guarantee actually works. So if you're having the Windows subsystem for Linux 2 on your Windows machine, then you are supposedly able to run Linux containers as well. So you basically just install, for instance, Ubuntu under WSL2, and then you should be able to run Docker from it in there. Not that this would be very efficient if you're not running it natively, sort of like on a Linux box. How do you actually create an image? Well, that's really, really simple. You have a Docker file, then you call build, and you get your image, if everything works out, of course, and there's no errors and whatnot. And the Docker file is really just a simple text file with instructions, and that makes it also nicely to be added like under Git or any other subversion, sort of like version control system. So where you can then track over time various versions of your Docker images. And below you can see, I presume you can see my mouse cursor. So you have basically your from statement. So this is a simple Docker file out content where I'm just packaging our Y-Annotations Python library. So with from, I specify what my base image is. In this case, it's Ubuntu version 2004. And each run command is basically a Docker layer that you're adding onto the base image. And the idea is to make these as lean as possible. So anything that is temporary, you should remove again. So in this case, the Ubuntu 2004 image won't have any package information on the system, nothing cached. So you actually have to first do an update before you can store anything. And then also to keep it lean, you also remove sort of like, please don't install any recommended packages and whatnot, and automate it with -y. Please just say yes, install everything that follows there. Basically Python 3 development environment, you can do something. And at the end, you sort of like remove anything that apt really cached there. Next, you can then run, since you installed Python 3, you can of course then also run pip3 for installing Python 3 libraries. And once again, you install them without caching locally. So in this case, I'm installing NumPy, and then beyond there also a particular version of Y notations. And that's also sort of like best practice. You don't just want to install necessarily the latest. I mean, here I'm doing a little bit of a naughty one. I just define a lower limit. However, that could run later on into problems if there's a new NumPy version that breaks things in my library. So fixing that to a particular version is usually a recommended way. But just showing you that you can have all kinds of arbitrary things in here in your run command. So this is basically a Linux command that would run on the command line. Just the run as a Docker instructions. Here I'm creating a directory, and if you, of course, rather than just grabbing things from the net, you can also just copy things from your local context with the copy command. So here I'm basically just inputting a little customization how my bash section looks when I'm logging in to a container. So rather than having nothing in there, no customization, it can be sometimes a bit confusing with which Docker container you are. Having this customized output, what this is, it can be quite helpful. Work directory just basically says, instructs Docker, hey, okay, I'm switching to this directory. If it shouldn't be there, it will automatically create it. So really, really simple. Anyone who's ever worked with a particular Linux distro will be quite familiar with these. All these instructions basically run under sudo. You are root in this case for installing things, so there's no sudo or other things necessary. And that basically sets up your image. And each of the layers will get a hash. And if you have common commands in there, then this could, for instance, anything Ubuntu 2004 and that following set, if you reuse it for other ones, then this would be sort of like a particular layer that would get reused among images. But that's, disk space is cheap, so don't worry about that too much. The most important thing is to make downloads quick, remove anything within a layer that is not necessary. So any build environment, make sure that you clean up afterwards again. So building, as said earlier, you just basically call build. So Docker is your main command. Then the subcommand is build, and you're running it within the directory where your Docker file is. So you can just give it a dot. And of course, you also tag that. You give your Docker image a name rather than an automatic generated. It's far easier to remember because they will, each time you run the build command, you will get a new name, which is a little bit confusing. So that's much easier. And for starting a container, instead of the build command, you use the run command. At the end, you once again refer to the tag of the Docker image that you want to run. So in this case, the one that I use for building. The -i means it's an interactive mode rather than just running a command and not having an interactive shell in there. And with -v, I'm basically mapping my current directory on the host onto the /workspace directory in the container. That allows me to use anything that's within the current directory where I'm in, plus anything below there. For instance, if I have data, models, or anything like that in there, I can use. In terms of base images, there are gazillions out there. Quite often people just fall back on Ubuntu, Debian, or Alpine. That's sort of like very common ones. You have sort of further sort of like built on that, you have then ones that NVIDIA provides for certain versions in combination with CUDA and cuDNN if you're doing deep learning. And sitting on top of that, TensorFlow and PyTorch images are then basically available as well. And then you can use those base images depending on what the application is, and then use that in your from statement, name of the image plus the version, and then build on top of that. And then you can, rather than just building it locally, you can of course also publish your images. So by default, you can do that on Docker Hub. There's a sort of like a limited amount that you can actually push out to, and if it's open source, it's less likely to be a problem. However, if it's commercially sensitive, or you're working with iwi or companies, or it's just really for yourself in-house use and whatnot, then you could also look at maybe having a self-hosted registry. So this is basically what Docker calls where things are being hosted. The Nexus repository is something that we are using at the Applied Machine Learning Group for deploying our own in-house or even other images, and that allows you to have access control. So that, for instance, multiple people can deploy to the same URLs, update images, rather than just a single person, like you would do with a personal account on Docker Hub. Last year, I wrote a little introduction, which is Docker for Data Scientists. It talks you through the basics, how you can use Docker. So I just gave you an extremely limited overview of what it can do. I'm going to move over to deep learning now, but I will put that link later on in the chat as well. And of course, there's the Docker documentation as well. Since Docker can do a lot, it's very overwhelming. That was one of the reasons why I actually wrote Docker for Data Scientists, because it really boils it down to those few commands that you really, really need to get away with to make it easier for your work. Now, for deep learning, how do you apply it there? Well, I've talked about already that CUDA and cuDNN base images are already being made available. So in this case, compared to what you normally do on the machine, you would get your IT department to install CUDA, cuDNN, and all kinds of other libraries on your host system. This is no longer the case, because this becomes part of your image and not of the host. And only the NVIDIA drivers, in order to make to get access to the GPU on your system, would need to be installed, nothing else. That can be then basically passed through into the host, into the container, and then whatever relevant CUDA or cuDNN version you have can take advantage of that then. And by pushing it into the container, you can finally write pipelines when you actually have conflicting dependencies between frameworks. If one requires CUDA 10 and another requires CUDA 11, then it's no longer a problem. Disk space is cheap compared to trying to update someone else's code so it works with a newer version of CUDA. And by having these images, you also want to have scripts that you can basically invoke from the console, so you can actually execute, whether it's training of models, inference and whatnot, or exporting of models. Then you basically just package them with your container. In terms of input-output, the simplest approach that we've used in the past and still use, especially for testing and whatnot, is file polling. To make things a little bit easier, I wrote a little Python library for that, which I've linked there. That allows you to really sort of like basically poll for files in the directory. So if you're doing batch processing of incoming images, for instance, and you want to do predictions with a build model, you can use that. So to make that easy. However, if you're using SSDs on your system, that will wear them out over time, especially if it's a production system that processes thousands and thousands of images a day. It's not the best approach. In order to do everything or most things hopefully in memory. You can sort of like rely on in-memory databases like Redis. So not has Python bindings, for instance, among I don't know how many hundreds of different programming languages. It's extremely well supported. And with that case, you can then basically just generate images, push them through on Redis, and your container listens on certain broadcasts, pulls the image from there, does processing, and then pushes it out on Redis again. And your outer sort of like, if you have a pipeline, then another bit can sort of like wait on another broadcast, uses those predictions and does something else with it and whatnot. And then at the final end of your pipeline, you get something out that could be then, for instance, be displayed again to the user. And the thing is, like I've mentioned a little bit already, Docker images are basically everything's layered, so they're like onions. So if you don't like a particular script that's not quite doing what you want to do, then you can basically just create a new layer. You basically use the from statement to use that particular image that does 99% of what you want to do as your base image, and then you basically just copy in your own script that does then exactly what you need for your own use case. Makes reuse of existing base images really nice. You don't have to rebuild everything basically from an Ubuntu 20 package. You can, but you don't have to. And that makes it quite quick in deploying new images and containers then in the wild. And do you have to really do things from scratch? Yeah, not really. So we in the Applied Machine Learning group have gone through the pain of actually creating Docker images already for a while. Mostly me, I admit, but last month I finally finished, actually the start of this month, I actually finally finished a set of tutorials for various data domains where it's basically taking you through, and I'm going to demo that shortly, how you can use our existing Docker images to build models and also apply them. And the domains that I've covered in those tutorials at this stage are basically as simple as image classification, where you just classify whole images with a label, object detection, which is predicting bounding boxes within an image, giving it a label, image segmentation, where you do pixel level classification, and instance segmentation, where you determine masks or polygons within an image of objects, for instance, people or whatnot. Useful tools, and of course, I'm going to advertise our tools here as well. Adams is something they've developed for over 10 years now. It's mainly a workflow engine, contains machine learning libraries like Weka, Moa, and Mecha. But in this context, it's mainly for annotating images. So there are workflows available that you can use for object detection, instance segmentation, and image segmentation that support you with that. So you can use your raw data and annotate things and then build models with the annotated data. And since there are unfortunately a gazillion of different versions of data sets out there, for our user-friendly deep learning MVIE project, which started 3 years ago now, we noticed we definitely need some form of library that allows you to convert between various formats. And that's the Y annotations library. You can not only convert between formats, you can also do like data augmentation, filter data, and also generate simple statistics, depending on the data domain. And that's sort of like, we have some video support in there, we have image processing, image annotation, of course, and a little bit with audio as well for whether it's audio classification or speech to text in there. Okay, so that's presentation-wise everything. Are there any questions? Before I head into demo time? No? Okay, cool. All right, I'll post that link later on. So this is the Docker for Data Scientists intro. And what I'll be talking through is the applied deep learning tutorial set. I'm just going to look at object detection, and I'm going to look at YOLO v5. So there's also a video here and what flows you can use if you actually want to start with a data set from scratch. I'm not going through that for the time being. I'm going to use an existing data set, which I've already downloaded. YOLO v5 is nice because it's a very fast object detection and relatively light on the memory consumption framework that you can also run once, for instance, exported to ONNX, an interchange format for neural networks. You can also run it, for instance, on CPU as well, which makes it nice if you want to run it like on IoT devices. So in this case, I'm using the American Sign Language dataset. So there's basically our 26 letters in sign language, and they got annotated with basically where the hand is. And that's basically where we're trying to build a model with. So I've already downloaded that data set. I'm over here on the server. I've unpacked it. However, it is not in a format that I can use. So it's not in the YOLO format. It's in a Pascal VOC format. So I'll basically run a, of course, Docker command, which uses our Y notations library. So in this case, it loads from VOC, and that's basically our input here, and then converts it to YOLO. And in this case, it also automatically splits it into train, validation, and test with a 70-15-15 split. So all these things are built into our Y notations library to make that actually quite nice and easy and simple for generating datasets in different formats, so you don't have to write custom scripts all the time and then or adapt them. So I'm just logged in. So here's my American Sign Language letters, which I've unpacked. That's in here. So if I go, you'll see, you can see there's always an XML file with an associated JPEG. I'm just going to go over there, run this command line. It takes a little wee while, so if there's any questions, I could take some now. It runs probably for a couple of minutes. So these instructions basically take you through from everything, from download, from how you can annotate data, you can retrieve your own, you can already use pre-existing data sets that are available for download, and through here like data conversion. And I just have to fix something that's still a bug. Well, not really a bug, but I have to remove some empty directories. Okay.
Wait.
Yes.
Peter, just sorry to disturb. So
Yeah.
this is the set that you haven't yet split up, or you haven't yet specified the train, test, and validation sets, or you have to specify them before you come to this step?
So the command. So this was basically just what I downloaded had VOC, Pascal VOC annotations in there. So that's already annotated. I don't need to do anything. However, it's just one blob of data. And with this command that I've executed, it basically reads the data in VOC format and outputs it in another directory. In this one here, we can have a look at that one then. And does also a split in here. So if we go on images, we can see that we have train, test, and validation then in there.
So how does it select? Does it just randomly select?
Yes.
Yes. Okay,
yeah.
right.
And you can also specify a seed value as well, if you want to.
Yeah. Thank you.
I mean, otherwise, if you already have a data set where you have a predefined split and whatnot, then you would just run the conversion basically on each of the subsets. But in this case, I have one large pool and I want to sort of like split it up. I mean, some of the libraries do the splitting between train test and validation themselves. In this case, YOLO doesn't, so I have to basically do that for it. Cool. I need to, for YOLO, I need to create there. I need to download a little dataset description and modify that. So, because since the labels of the so the labels that the output is seeing depends on the order of images. They might not be ordered from A to Z. So I'm basically cutting out what labels. So I was also outputting a labels txt file, so I know actually in what order they came. And for YOLO P5, it needs a description of the labels. So I'm basically just outputting that with a little command, so I can just bung that into that YAML file. So just changing that. So that's the actual order in there. So here you would also have to define like the number of classes. So this is for a training exam, so I know it's going to be 26. I just don't know how, in what order. And here's sort of like predefined directories where, so you can see workspace. So that's pointing within my Docker container into this particular data set, and where it basically finds train, validation, and test images. Just one of each framework has its peculiarities how to run it. So they're not just necessarily just with command line parameters. Some are purely command line parameters. Some use a mix of config files, and some are pretty exclusively only with config files. All right, so we use our pre-existing sort of like Docker image that we published on Docker Hub. I will then kick off the learning. So in this case, I can just quickly go through things here. So I'll basically map my user and group ID into the container. I increase shared memory a bit. I tell the container, please make all GPUs available. Most cases, since we're poor, we only have one on the system, but you could specify which particular GPU you would want to run it on. Like in engineering, I think, have a multi-GPU machine. So if you want to train multiple models on there, you would specify what particular GPU you want to use. Once again, I map my current working directory onto /workspace. Here in non-interactive mode now is my Docker image. And since it's non-interactive, I basically call YOLO train with particular image size, batch size, how long I want to train, and so on. And then sort of like where my dataset description is, a pre-trained model, which I already downloaded. So that's one thing that other frameworks do automatically. In this particular YOLO framework that I'm using, you actually have to download that yourself, what you're using there, and where to store the output under what directory name. And that then basically starts the Docker container. YOLO train gets started. It looks at the data set, evaluates that. It does some plots and whatnot, and then basically runs for 20 epochs. And the nice thing about YOLO is it really trains fast. And if it's a simple enough problem that you're looking at, like for instance, identifying people or cars and whatnot, then this will actually work quite well with relatively little training data. And in this case, we're looking for hands, so that should work quite well too. So that's going to train a little bit. If there's more questions, I will probably have 3 or 4 minutes time. So the training's done before we can export the build model and then actually make predictions with it. Any more questions?
You can start entertaining us with some singing while waiting.
I don't want to freak everyone out. And because then it would be just me in the Zoom session, so I'd rather not.
20 epochs. I mean, I guess stupid question. Stupid question here. It's YOLO, so we can't, but it's Dockerized. So theoretically, somewhere in there, in these layers, we can go and try to be funny and change an activation function somewhere.
You see, I think with that particular YOLO v5 version, it is a particular network architecture that's optimized.
Yeah.
So all you do is basically just then doing transfer learning. You use an existing pre-trained network and then apply it to your net and your particular problem. If
so is all layers, or have you frozen some layers in it?
okay, that was from the robotic overlords. Can you get closer to the mic?
Is it trained all layers on your new data, or have you frozen some layers?
So the first two words I understood, and then it lost me again. So you can train it on your data, yes. So that's basically what I'm doing here with transfer learning.
Yeah, but have you frozen some layers? Have you unfreezed all layers?
So I'm not quite sure with that particular what's unfrozen. So depending, so I'm not 100% sure what that framework does internally. It has a lot of command line options as well. I didn't need to do anything else. With some other frameworks, you can specify what layers you want to freeze and what not, and what to chop off. So it's really up to you. So the tutorials talk you here really just through use existing architectures rather than creating your own.
Right.
So you can always come up with your own architectures as well, if you really, really want to. But what I've found out most of the time, if you're doing like anything in the image processing domain, it will, most of these algorithms that are out there, you can actually use straight away. There's not necessarily a lot of tweaking necessary apart from the image dimensions that you're using, the number of classes that you're trying to predict and things like that, and maybe some data augmentation really. Most of the time, it just works like that. So you don't actually have to tune too much with your layers. And I presume when you're doing transfer learning, most of them will probably just chop off the last layer and adapt that based on the number of classes that you actually have. So if something's tried on MS Copal, it would have 80 classes. And if it's ImageNet, I think there's around 1,000 classes. And then really just chopping off the last layer. And then that's what you put in.
What sort of GPU are you running on?
So this is just a 2080 here. With 2080 Ti with 11 gigs of RAM.
Just.
Yeah, it's nothing fancy. I mean, this is out of date. So later this year, the 4000 series will be released.
Yeah.
I mean, what we found from the 1080 to 2080 was probably only like a 15% speed increase, but for quite a hefty 50% price increase. Which wasn't that great. I mean, it was all the ray tracing and whatnot that came there, where they put so much emphasis on it. I mean, not something that we are using. What was quite interesting is with the 3000 series, so we have a 3090 that has 24 gigs of RAM. It's not so much the speed, but being able to have larger batch sizes for training, that actually helps. So I've noticed with some of the problems that I wasn't actually getting very good results with models, and my suspicion is that this is mainly due to the small batch size that I had to revert to because I only had 11 gigs of RAM to train in. Because most of these algorithms come from Facebook or Google or other large corporations like that that can just chuck enough money at their data centers where they then have usually clusters of large GPUs like this one is an A100, I think, that the machine learning group has, and they have basically lots of these ones. And most setups really want, oh, you're using 8 GPUs. No, I'm actually only using one. Thank you very much. Cool. But coming back, I mean, to YOLO, you can also train this really on your laptop, for instance. It just takes a bit longer, but you can definitely train it there as well. So this model has finished training. If I am looking on the server, I can look, for instance, at a confusion matrix that this nicely generates. So you can see it's doing actually quite reasonable. It has some misclassifications in there, but some of them it's doing actually really, really well. So J seems to 100%, Q 100%, and L is doing well as well. So not too bad here. All right, quick export. So the advantage of ONNX is that you can then use an ONNX runtime environment to use that particular model. You don't have to use the existing YOLO framework anymore. If I'm just okay, so I'm just going to copy YOLO split from the test. No, just test. Okay. Into a directory, and I just want to run predictions on there. And in this case, it's using file polling, and there's a different script, YOLO v5 predict poll in this case. I'm still using the CUDA one, which is not necessary. I'm just sticking with the same image unless I'd have to download another one. I refer basically to my ONNX model. I still have to point to my dataset description and what image size I'm using basically for description. So it doesn't seem to store that within the model itself. So here's some meta information that you need to know. And then I basically just process everything that's in the input directory and chuck it in the output directory. So the thing that's slowing things down is actually getting things via SSH back. So you can see a single prediction is somewhere 20-25 milliseconds per image. I mean, it's a relatively small image, 416 square. But I can then just have a look at, I might actually just zip that. I copy this across. Go on my Adams preview browser, which then actually overlays the predictions onto the actual image.
Oh, that one is the magic. Oh, that one's very beautiful, by the way.
Oh, I have it in here. Why is it not? Oh, here we go. So I'm just looking for JPEGs. JPEG. Predictions. Yeah, so I'm just going to customize it a bit. Yeah, so you have an A here. I mean, it's easy to confirm that it's an A because it's also in the file name. If we go on G, there's a G here, there's an I, here's an L, an N, and you can see here's a, it should have been an S, but maybe it was too fuzzy and I thought it was an A. In this case, should have been a T, but it's an M. So it doesn't get everything right. V and W seems to be a little bit confused, understandably here. So certain things most likely based on, so it was only 20 epochs. So we have to give it that. If you train that for longer, for instance, like 100 epochs, then you probably can do something with that as well. And but yeah, so if you're looking, the nice thing is YOLO creates nice sort of like outputs with your model, so you can see like the distribution of how many instances for your various classes have, where they are, height and width sort of like distributions, which is quite helpful. You can also see sort of like results, sort of like you can still see that the losses are still going down quite steeply, so it would be quite possible if you up it to at least 50 or 100 epochs that you actually then only finally see plateauing out, and then you could have something with that. Okay, so that basically concludes that little intro, how you can sort of like use Docker to actually package things. And if you don't, especially if you have students that want to get going with some simple object detection or instance segmentation sort of like projects, they could basically just use these pre-existing frameworks, figure out with these tutorials how to get going with it and how to annotate data and actually get some models started that they can actually then use and practice, rather than spending days or weeks on it trying to get a framework going and then figuring out how the framework works. And that concludes my presentation.